All right, so I think what I'm going to do for this, I'm going to go over a couple of things I found for equilibrium. So I found a few multiple choice questions, and then I have an FRQ. So I'm going to go over that, and I did post it under updates. So if you wanted these questions, like it's under updates. I didn't want to post it under material because I didn't want anybody to think they had to do those. Okay, so I went on the demo. Did everybody see that I put a link in to get to the demo for uploading? Okay. Yeah, so I'm going to send out more information about that, but like you guys have to go and test it, because I went on there and I thought, okay, I'm going to take a photo and upload it on my computer. Well, I airdropped it. Like I timed out on the first question because I couldn't figure out how to get to the photo. Like it has to be a JPEG, and then apparently when you take a photo with your phone, it's not JPEG. So you guys have to go and actually attempt to do it and try to do it multiple ways, and I'm going to have something like as an assignment for that. Okay. Does anybody have any like questions or anything that you guys want me to talk about really quick? And then I'm going to go over some of the stuff with the equilibrium. All right, so under the survey that I gave, between my classes, equilibrium and FRQ help was pretty much tied. So I'm just gonna talk about these couple of questions because I think if they're going to ask you an equilibrium question, I feel like, because there's only 2 questions, they're going to try to integrate gas laws. Because then you could integrate gas laws, you could have Dalton's law, ideal, and then have an equilibrium question all kind of wrapped into one. So I found a couple of things. Now, these are multiple choice, but I thought they were worth going over. So if you look at the question, it says that you have the synthesis of CH3OH, so methanol, from carbon monoxide and H2, and then this is our reaction. The value Kc is going to be 14.5. So automatically reading that, Kc is larger than 1, which means that this reaction is more product favored. So you're going to have a lot more products than you will reactants for this. It says that we have a 1 mole sample of carbon monoxide and a 1 mole sample of H2. So you have equal amounts are pumped into a rigid, previously evacuated 2-liter container. The reaction is at this temperature. So which of the following is true at equilibrium? So if we're looking at this, it's giving you, or asking you to compare equilibrium amounts. So one of the things that we could do here is go ahead and set up an ice table. Okay, so now it says that we have a 1 mole sample of carbon monoxide, 1 mole sample of H2 in a 2-liter container. It gives the volume here, so you do have to account for that. Not that it really matters with this particular question, but if you had an FRQ and it gives you the amount and it also gives you the volume, you're going to want to go ahead and calculate that out. So 1 mole divided by 2 would be 0.5. Same thing over here. It's 0.5. And then, of course, for a product, we should have 0. The reaction hasn't progressed yet. So then, if we have 0 products, we're going to be adding products. So it's plus 1x. This would be minus x. This would be minus 2x. So at equilibrium, I'm going to have 0.5 minus x, 0.5 minus 2x, and then just x here. All right, so looking at this, if you're just comparing the amounts, well, I know that this should be smaller than this since I'm subtracting 2 times the x value. So I do know that H2 has to be smaller than my carbon monoxide. It takes twice as much H2. So I know that this is definitely a possibility. H2 is going to be smaller than CO. Okay, so let's look at the other choices. H2 is twice that, or carbon monoxide is twice that. Well, you don't know the value of X, so you can't say that. Carbon monoxide is equal to the methanol. Well, that's definitely not going to be true. One is just going to be the value of X. The other one is going to be 0.5 minus X. And then that's presented for both of those choices. So it is going to be that the H2 is going to be smaller than the carbon monoxide. So with this, we set up an ice table and we're looking at those values. We're just comparing them. Now the next question, and I put this in here. If the total pressure is 1.2 atmospheres at equilibrium, what are the partial pressures of each gas? Okay, so one thing that you have to remember is that if you have a container full of gases, each gas has its own pressure, but all of the pressures added up together are going to give you the total pressure. So if at equilibrium the pressure is 1.2, you want to know the partial pressure of each gas. Well, okay, let's go back. Let's set up our ice table again. Okay, so remember, you have Kc, which deals with concentration, and then you have Kp. Okay, Kp is equal to the partial pressure of the methanol divided by the partial pressure of the carbon monoxide multiplied by the partial pressure of H2 squared. So this is Kp. So when you have Kp, you're looking at partial pressures. When you're looking at Kc, you're dealing with the concentration. So with the Kc, what we just did, we had to account for the fact that we had a 2-liter container. This, if we're looking at partial pressures, I don't really need to worry about the size of the container. What I need to worry about is how much of each gas we have in here. So remember, pressure is a result of collisions against the container. So I have equal amounts of carbon monoxide and H2, which means that they have equal pressures. So I'm going to set up my ice table again, but I'm going to use 1 to start off with, because each molecule or each mole of molecules will present it or give pressure by colliding with the container. So now we have 1 mole for each. So the change, it's still the same thing. You're going to subtract x, subtract 2x, add x. So at equilibrium, it's 1 minus x, 1 minus 2x, and then x. Well, this represents the partial pressure for each gas. And I know that the total pressure is 1.2. Well, the total pressure should be equal to the pressure of the carbon monoxide, the pressure of the H2, and the pressure of the methanol added up together. Well, let's go ahead and plug all those things in and set that the sum of these 3 things is equal to 1.2. So 1.2 is equal to 1 minus x plus 1 minus 2x plus x. Partial pressure of the CO plus the partial pressure of H2 plus the partial pressure of the methanol. Well, now you just put everything together. My negative x and positive x will cancel. 1 plus 1 would be 2. So 2 minus 2x is equal to 1.2. So now you can just solve for x. So 1.2 minus 2 would give me negative 0.8. And then at this point, you would have X being positive 0.4. All right, so now the partial pressure of the methanol would just be 0.4 atmospheres. And then for H2, it'd be 1 minus 2 times 0.4. So that would be 0.2. And then this one would be 1 minus 0.4, so 0.6. That would give you the partial pressures. So I could easily see on this particular test them combining Dalton's law with an equilibrium problem, because then you get more concepts tested. Does that make sense to everybody? All right. Okay, so the first part, if we look at the question, it says I have a 1 mole sample of this, 1 mole sample of this, and it's a 2-liter container. If I'm talking about KC deals with concentrations, so you have to account for the fact that it's in a 2-liter container. Now, for this particular question, did I really need to do that? No, I didn't, because it's just asking you to make a comparison. But if I wanted to get the concentration for each amount, then I have to account for the fact that it's 2 liters. Now, if they don't mention the volume, you can assume that the volume is just going to be 1 and you don't need to worry about it. But because it's mentioned here, I'm going to go ahead and divide my 1 mole by 2 liters to get me my concentration. Yeah. So for Kp, that doesn't matter because we're looking at partial pressures. Okay, so the next question is the same prompt. Okay, and then, so it's the same reaction. It says that a mixture of CO and H2 is pumped into the 2-liter container. The total pressure is 1.2 at equilibrium. What will the total pressure of the system if the volume goes down to 1 liter? Okay, so the thing is, if this was not an equilibrium system, okay, so knowing what I know now, it's an equilibrium system, so it goes back and forth, okay? If you were to change the volume on this kind of system, because it's gaseous, the volume changes the pressure. So remember, this is Le Chatelier's principle. Whatever's done must be undone. If you change the pressure, it's going to want to shift to either relieve the pressure or create more pressure. So I know that normally, if it was just a normal system where like it's not shifting back and forth, if I reduce the volume by half, I should increase my pressure by a factor of 2. But this is an equilibrium system, so it can shift back and forth. So knowing what I know, if the volume goes down, the pressure should go up. Okay, so it's definitely not going to be less than the original pressure. So it's not going to be less than 1.2. That's not going to happen. Now, knowing that it's an equilibrium system, okay, I've increased the pressure. Well, what does it want to do? It wants to decrease it again. So it's going to go to the side with less moles to get rid of some of that pressure. So it's going to go to the product side to relieve some of that pressure. So I know that because it's an equilibrium system, it can't be double, because now that I've changed the volume, I'm going to want to shift to undo that. So it can't be 2.4, it can't be twice. So it will be somewhere between 1.2 and 2.4. Can I solve for that? Yeah, but they won't ask you to do that. I don't think they'll ask you to do that, because then you would have to do a quadratic. So essentially what you would have to do if you were going to solve for that is you would set up an ice table again. So I'm going to show you how to do that, but I really don't think for this particular one, because K is so large, they're not going to want you to do a quadratic. That's going to take up too much time. So if you know that the volume goes down, okay, so right now, I know that my pressure, my initial pressure, because I just solved for all those, this is 0.6, this is 0.2, and this was 0.4. Okay, I just solved for all those pressures. So this should be the pressure at equilibrium before I changed it. Okay, so initially this is what it is. Then I changed it. Okay, so now I know that I'm actually going to shift my reaction again. So I'm going to try to get rid of as many molecules as I can. So it's going to be minus x minus 2x plus x. So it'd be 0.6 minus x, 0.2 minus 2x, and then 0.4 plus x. So you could put this into the Kp expression and solve for little x, but that will require you to do a quadratic. So that's not going to be a thing. Not for this exam. Okay, so let's look at the FRQ that I pulled. All right, so we have this reaction. Carbon as a solid plus carbon dioxide produces carbon monoxide. It tells you that you have a temperature, it gives you a volume, and then if you look, it gives you a data table with pressures. Automatically your head should be going off, and ideal gas law should be like in your head. Probably going to be using that somewhere. Okay, so write the expression for the equilibrium constant for Kp. Okay, so be careful when you're doing this. Okay, when you're writing for Kp, it's partial pressure. Don't put the brackets. So Kp would be equal to my products, so the partial pressure of CO squared, divided by my reactants. I don't include carbon. Carbon never, or not carbon, but solids never get included. And then the partial pressure of the CO2 to the first. So that's my Kp expression. Now it says calculate the number of moles of CO2 initially placed in the container. So we're looking for N, and this is initially. So they love data tables. Initially, so before the reaction starts, the pressure is 5. Well, if I look before the reaction starts, I don't have any CO, I don't have any products. The only thing that can be contributing to the pressure should be the CO2. So the pressure is going to be 5. So I'm looking for the number of moles. Well, I know what the pressure is. The pressure is going to be 5. Volume is 2. The number of moles, well, that's what we're looking for. It's the ideal gas law constant. And then temperature is 1160. So now just solve for your number of moles. So your number of moles here should be 0.105. All right, so now you have your number of moles, and remember this is for the CO2. Yep, CO2. All right, so for the reaction mixture at equilibrium, the partial pressure of CO2 is 1.63. Calculate the partial pressure of the CO and the value of Kp. All right, so anytime that you are looking for the value of Kp, you need the equilibrium amounts. So I'm looking to get Kp, which means I need the partial pressure of both of them, and I only have one of them. So that means I need to go ahead and do an ice table. Okay, I don't care about this, it's a solid. So initially, okay, and we're looking for Kp, so again, this is going to be the partial pressure. Initially, the partial pressure of CO2 is going to be 5. Okay, that's what I get from the data table right here. Initially, I should have 0 products. The change, well, this should be subtracting. I'm adding, so this is going to be 2x, and at equilibrium, this should be 5 minus x, this should be 2x. Well, it gives me one of the amounts at equilibrium for the CO2. It tells me that it's 1.63. So can I solve for x? Well, I know that 5 minus some number gives me 1.63, so yeah. 5 minus 1.63. Okay. So I'm going to subtract x on both sides and divide by negative, because you should have a positive number here. So x is going to be equal to 3.37. So I have x. Now let's solve for the partial pressure of this. It should just be twice that number. So 2 times 3.37 would give me 6.74. So that's the first part. You needed the partial pressure. Okay, so now it's asking for the value of Kp. So now I'm going to plug everything back into the K expression. So Kp is equal to the partial pressure of CO, which we just solved for. It's 6.74 squared. All right. And divided by the partial pressure at equilibrium. Be careful here. It's not 3.37. That's x. It's this. It tells us that it's 1.63. All right. So Kp is equal to 27.86. And remember, there are no units for K. All right. So any questions about what I just did here? Any questions? We're good. All right. So the next part says, if a suitable catalyst were placed into the vessel, would the final total pressure of the gases at equilibrium be greater, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst? Okay, here's something they do a lot. They kind of try to integrate kinetics with equilibrium and make sure that you understand they're two separate topics. Kinetics is about the rate of a reaction. Equilibrium is about what you should have for your products versus your reactants. Now, if you put a catalyst in something, okay, well, it makes the reaction go faster, so you get to equilibrium quicker, but it doesn't change how much you're going to produce. So technically, nothing changes here, not with equilibrium. You're also not going to produce more gases, because that would be the amount of reactants that start. So if you wanted to make more of something, you have to start off with more reactants. So this question right here is just kind of testing, do you understand that catalysts have nothing to do with equilibrium? You get to equilibrium faster, but it has no bearing on equilibrium. And then the last part, it says, in another experiment, the same reaction, in a 2-liter container contains 10 grams of carbon plus CO plus CO2 at a partial pressure of 2 atmospheres. Predict whether the partial pressure of CO2 will increase, decrease, or remain the same as the system approaches equilibrium. All right, so we know that the value of Kp is about 27. Okay, it's asking, essentially what it's asking is if you're going to make more CO2 if your partial pressure is now 2. So it's giving you an amount for the partial pressures, and it's asking you, okay, so are you going to increase your products or are you going to increase reactants? This is a Q versus K problem. So what you need to know is what is the value of Q, because we have 2 atmospheres of pressure now, okay? So we need to know how big is Q, and then we're going to compare it to the value of K, because we're always trying to get back to K. So Q is equal to the partial pressure of the CO squared divided by the partial pressure of the CO2. So let's see where we are. So Q is equal to 2 squared divided by 2. So Q is equal to 2. Okay, well, now let's look at what K is. K is about, I think it was about 28, 27. So now draw out your diagram. Okay, Q is 2. Well, it's less, so it's on the bottom. It's less than K. Okay, so if Q is less than K, we're going to shift to the right side of the reaction. We're going to shift to the product side. We need to make more products to increase that value. So, if I look at the reaction, I have carbon monoxide on my product side, CO2 on my reactant side. It's asking whether the CO2 will increase, decrease, or remain the same. So we know we're going to shift towards our product side. We're going to use up reactants to do that. So CO2 should decrease. So if you're answering a question that involves Le Chatelier's principle, which this does, talk about Q versus K. So if you know the value of Q, if Q is less than K, then you need to shift to the product side. And then that means the CO2 will decrease. Don't make sure that you don't just say that it shifts to the product side. It's asking whether CO2 will increase, decrease, or what's going to happen to that. Make sure you address that and then explain why with Q versus K. Okay, any questions about what any parts of this FRQ or any of the stuff I just talked about? Okay, are there any other questions that you guys have for me now? Like about anything, like including the exam? Okay, the topics that aren't going to be on the exam, they cut off the last 2 units. So electrochem is gone, and acid base stuff. So okay, they can ask you basic things about acid bases. So they can ask you about a titration. They can ask you pH calculations, like basic pH stuff. What they should not do is they shouldn't have anything with like Ka or Kb or buffers. Okay, those things shouldn't be tested. Electrochem should not be tested. Can they test redox? Yes, absolutely. But asking questions about like electrochemical cells, that shouldn't be happening. Also, calculations with Gibbs free energy. I think they could potentially ask you about delta G, or well, really more about delta S, because that's integrated in one of the other topics, but more of like a conceptual question, but not a calculation question. Yeah, no problem. Also, I'm going to be uploading like 3 documents that I think are going to be helpful. One of them covers calculating different things with thermo, okay? You won't be asked to calculate Gibbs free energy or calculate entropy, but I think I've included some of that stuff on there, so just ignore that for this test. I also have another sheet on basic lab setups, and then I have another PowerPoint that talks about how to answer FRQs. So I'm going to upload those probably sometime today, and I kind of advise you guys look through them. So it's not really extra work for you to do, it's just stuff for you to kind of look through, and helpful guides essentially. Okay, Lewis structures should not be asked. No, you shouldn't have to draw Lewis structures or particle diagrams. That's what at least we were told, but you know, or that's what I learned Tuesday night. Yeah, no problem. So I'm not going to hold you guys here if you have other things you need to do, but if you have questions, just let me know and I'll stick around for a little bit longer. You too.
You are currently the only person in this conference.